All right. Well, I hope that everybody's having a good day, good week so far. If you have not turned in your homework yet, try to get that to me, as soon as you can. Remember, it is not for a grade. I am going to be keeping track of it in Teams, though, the grade book, just in case anybody needs a retake. Tomorrow is when we're going to take the quiz over that material. So if you have any questions, come on in. Friday by 8:05 a.m., remember that's the deadline, so the window is closing for the Algebra 2 Skills sheet last week. I'm having several people come in every morning. If you're one of them, thank you so much. But if you still need help, let me know. And I know there were some people who asked about a pass, so don't let me forget about that. What is happening next Thursday? We have our exam, okay, so definitely something, we can go ahead and start looking at. And again, not a whole lot of time per night. I recommend, maybe 5-10 minutes. Just look over the material. If you feel good, fantastic. If not, come on in. Let's get some clarification. I've always thought that was a better way to kind of build up to it than do like a, 2 or 3 hour study session the night before, okay? So any questions on that? Okay. Now, I also want to go ahead and make you aware there are several lockdowns, drills happening next week that I want to go ahead and make sure you're aware of. Okay, so on Tuesday, the 27th, we're going to have our first fire drill during first period. So hopefully your first period teachers have already started telling you where to go in case of an emergency. Is that right? Okay, some people are shaking their heads no. Hopefully that will happen sooner rather than later. Let's say that the fire alarm goes off during this class. What do? Okay, so we're going to leave our stuff, obviously. We're going to go ahead and go down these stairs right outside my room, past the nurse's office on the first floor. We're going to go out to the sidewalk. Now, we're not just going to stay at the sidewalk. Where are we going to go? There you go. Once we get to the sidewalk, we're going to go ahead and walk all the way over to the east parking lot where the band practices. And at that point, I'll get out my phone, navigate prepared. I'll go ahead and check roll. So make sure you find me, okay, so I can do that. Otherwise, I'll have to say, okay, he was in class, but I don't know where he went after we evacuated the building. So that's happening on Tuesday. On Wednesday, we're going to have 2 additional drills. During your fourth period class, we're going to have a lockout drill. Now remember, that's the one business as usual. Maybe something is happening near campus, down 19th Street, whatever the case is. But the building doors are going to be locked. The classroom doors will stay locked. We're just going to continue about our business. That's going to happen during fourth period. During seventh period on Wednesday of next week, that's when we have a lockdown drill. Okay, now the lockdown drill is if there's a threat, some kind of danger on campus. So if there were to be a drill or a situation, God forbid, during this class, what we're going to go ahead and do, and this is a somewhat, large class, we're going to kind of ask you to kind of forget about your personal bubbles, being close to each other. We're going to go ahead and group right over here against the wall by Lane and Fernanda. Okay, we definitely want to be out of sight of the windows, away from the doors. I'm going to close these blinds, and I'm going to ask you stay quiet and that you stay off your phone. Why would we ask you to do that?
Lights.
Someone talk?
So they don't see lights.
Well, this window is going to be closed. The door's locked, so we're going to try to keep it quiet. They shouldn't be able to see any lights. Okay, knock on wood. But what might somebody do if something like this actually occurred? Who might they contact? Parents. You're immediately going to start sending out texts or trying to call. We're going to ask that you not do that. Okay, the first responders who are going to come to the scene, they're going to have enough to deal with trying to figure out what the threat is, how to deal with it, make sure you guys are safe. So if you contact your parents, what are they going to do? They're more than likely going to drop what they're doing and come to the school. So it's going to make it way more difficult on the first responders if they've got, a couple hundred sets of parents who are trying to get in the building as well. Okay. So during a lockdown, at some point, your teacher's going to go ahead and tell you, it's okay, send a quick text message. I'm fine. We're in lockdown. More to come. Just a quick little message letting them know you're okay. All right. Any questions about that? Okay. And then next Thursday, we're going to have our exam, but what's happening 8th period? We have our first pep rally. Okay, we've got our first pep rally. So there's a lot of stuff going on, next week. I just want to go ahead and make sure you're aware of that so there's no surprises. Any questions, concerns about anything I mentioned, both here or campus-wide? Okay, cool. Well, let's go ahead and continue. On days that we have homework due, I'm going to go ahead and ask you just go ahead and turn them in. In fact, if you know the homework's due, if you just want to go ahead and put it in the box, go ahead and do so. I'll give you the opportunity to ask questions. I know we did this yesterday. Are there any other questions about the assignment we'd like to discuss? Number 19. Okay, now number 19 is actually very similar to number 20. If you're given an expression that can be simplified, I would recommend that you simplify before you begin to classify it. Because -6/3 is -2, right? Now let's start with the hierarchy. Is it complex? Yes. Okay, so it's complex. Real or imaginary? Real, okay, because the imaginary represents the BI term, okay, and there's no imaginary unit here, so it is real. Now, rational or irrational? Definitely rational. I mean, if you're looking originally, it was a fraction, but -2 itself can be written as a fraction. So that is rational. Now, because you could simplify it, I can also say this is a what? I can say this is an integer. But can I say it's a whole number? No, I could not go any further. And that's the thing. Sometimes, if the expression can be simplified, we always want to look at the simplified version. If it cannot be simplified, if you got something like, these right here, then you just go from what you have.
Okay, but like a fraction with a negative number.
Or even a fraction. Well, let's say you have a fraction, even if it's improper or just regular, but there's no common factors. Like maybe if I were to give you -5/7. I mean, that can't reduce any further. So going through, this one would be complex, it would be real, and it would be rational. But that one could not be classified as an integer. Okay. All right. Anything else? Yes, sir. 20. Okay. Now 20, how would I simplify that? What? There you go. The square root of -25 is 5i. 5i times 2, there's 10i. Okay. So is it complex? Yes. Okay. Real or imaginary? Yeah, that's a pure imaginary item. We don't have a real value adding or subtracting this. Okay. So once we classify it as imaginary, there's no further subgroups. We would stop there. Okay. In fact, does anybody remember what do we use for the irrationals now that we're saying I is imaginary?
Q.
There we go. A few people heard it. You can say R minus Q. You could also say R\Q. Preferably, I'd say R minus Q. Okay, but if you actually want to write out irrational, I'm not going to say no to that. Okay. All right, good. Does that make sense? What else? Oh, presumption. If it was 5 plus 10i? 5 plus 10i. Yeah, technically that one would just be complex. I mean, it has real and imaginary portions, but by definition, yeah, we wouldn't be able to go any further. Mm-hmm. Okay, good, good, good. Anything else? You want me to do what? Scroll up. Yes. I mean, in that set, I wouldn't go ahead and include 0 because, we have a distinction between even and odd numbers. If you're going to go ahead and classify it with an expression, then we could say any odd number can be represented by, let's say, 2n, where n is just any integer. Because an even number, by definition, is divisible by 2, right? So if I know for sure that this is even, then I could guarantee it's odd. Interesting. Okay. By simply adding 1. So that would guarantee me an even plus 1 would always give me an odd. So in this case here, I probably wouldn't include the 0 on that. Like when it says the odd positive, I would probably just say 1, 3, 5, 7. Why couldn't I include the 9?
Because it's less than.
Because it says less than 9. There you go. Again, it's all in the wording. Okay. All right, so does that help out, sir? I probably wouldn't. I mean, 0 is divisible by 2. It's just 0, but making a distinction, I don't think we can actually say 0 is either even or odd. Actually, I don't know that. I'll look into it. I'll see if I can get a second opinion on that. But I would think that you would need to include it. Okay. All right. What else? Good questions. Good questions. Okay. Going once. Twice. Sold. All right, now if you do end up having some questions, definitely let me know. Come on in during tutorials. Okay. All right, well, let's go ahead and start moving into our next section. So for this, I'm thinking we'll probably have a quiz over this. I'm thinking probably Tuesday over this material. Okay, I might end up just posting something for piecewise functions because I don't know if we can fit one in before Thursday, but we should definitely be able to get piecewise functions discussed before then. And that's pretty much what is going to encompass the test next week. But let's see here. X equals the directed distance from the y-axis, while f of x equals the directed distance from the x-axis. So a lot of vocabulary you're going to remember from Algebra 2 again. Okay. The vertical line test is a visual way to determine if a curve is a graph of a function or not. A set of points in a coordinate plane is the graph of y as a function of x if and only if no vertical line intersects the graph at more than one point. Actually, let me get back here so I'm not in their way. Okay. All right. And then we have a concept that's kind of grouped together, increasing, decreasing, and constant. A function f is increasing on an interval if for any 2x values in the interval where x sub 1 is less than x sub 2, we have f of x sub 1 less than f of x sub 2. Well, think about our function notation for a moment. Okay, this f of x right here. Okay, what's always given to me in the parentheses? That's your x value. That's the element of the domain. That's what you're going to replace x with. So that's your input. So if x is the input, what's f of x? That's the output. See, you're plugging some value into a function we're calling f, and you're going to get a corresponding value of y out of it. So when we have this expression here, when we say f of x sub 1 less than f of x sub 2, well, we're really saying y sub 1 less than y sub 2. Okay? So based on what we're doing with the x's, where are the y values getting larger? Okay? Decreasing. A function f is decreasing on an interval if for any 2x values, x sub 1 less than x sub 2, we have y sub 1 is greater than y sub 2. When you're talking about this concept, you always go from left to right across your graph, from smaller to larger, because you want to see where the y values basically going to have a positive slope or a negative slope. Okay? But we always describe that using the x's. It's the y values that we're looking at, but we describe where that happens using the x's. Same thing here, a function f is constant on an interval if for any 2x values we have y1 equals y sub 2. Remember that function notation is just interchangeable with y. And now we have even and odd. Okay, what does that mean? A function f is even if for each x in the domain of f of negative x equals f of x. That means, let's say you have a function, an equation that would describe a graph. If I can replace every x with its opposite and simplify, if I get the original equation with no changes, that guarantees me we're dealing with an even function. And it's going to have symmetry with the y-axis. Let me give you just a real basic example. Let's say f of x equals x squared. What parent function is that? It's the parabola, it's the quadratic, right? So let's go ahead and apply this test. I'm going to replace x with its opposite. So x squared is going to become negative x squared. Well, what happens when you square a negative? It becomes positive. So see, even though I plugged in a negative x, there was absolutely no change when I simplified. That's what the rule is telling me. That tells me it's going to be even. And if you think about what it looks like, remember, here's the parabola parent. The vertex is at the origin. It opens upwards. So you'll notice it does have symmetry with the y-axis. If I could fold along the y-axis, the two parts are going to come together perfectly. We say they coincide. You know, what you should do when it rains. Coincide. It's never ending. Okay. All right. Now, what if it's an odd function? Okay. Here's the rule for odd. If I can replace every x with its opposite, well, if I then get the opposite of the original equation, that means that every term in the original has now changed sign. Okay? Yes?
Is it still considered even if the axis of symmetry isn't the y-axis because of translation?
Depends on the function. Okay, but typically we want to fold on the y-axis. So even after a translation, if there's no longer that symmetry, we might not be able to say it's even. Okay, so there are going to be exceptions. Okay, because you could translate it vertically and it would be just fine, but you translate it horizontally, then it's no longer the case. Okay, so let me go ahead and give you an example because I want to show you symmetry with respect to the origin, what that means. So let me go ahead and give you another graph. Does anybody recognize this? That's the cubic function. Okay, x cubed, right? Now, if I can take any graph, if I can just spin it 180 degrees, half of a turn, half of a full rotation, if I end up with the exact same graph, that's what we refer to with symmetry about the origin. So imagine this is just like a big fan blade. Okay, here's the center of it right here. If I were to go ahead and just spin it halfway, would I end up with the same thing? Yeah, absolutely. So this graph is definitely odd. It's symmetric with the origin. Okay, and if I were to go ahead and plug negative x into x cubed, I'm going to get negative x cubed. Okay, so any questions on that? So this is like the overview. Okay, and let's go ahead and get into some of these more concrete ideas. Use the graph of the function f shown below to find the following. I want the domain and range, and then I want to evaluate the function at certain values. Okay, so domain and range, this is simply asking you how much space does the graph occupy in your grid. Basically, how wide is he? How tall is he? Okay, the domain is, of course, your x's. The range is your y values. But here's my question. How do we know if the graph continues beyond what we see? You could have arrows. Anybody ever seen a dot, dot, dot? Things like that. There'll be some indication to let you know that it continues. This guy here, I don't see anything like that. So that tells me we have set boundaries. So I'm looking for his domain. I want to know how wide he is. So where does he start and where does he stop? He begins at -2, and he goes all the way to what? 4. So I like to write these in interval notation. So he starts at -2, goes to 4. How will I close these? Parentheses, brackets? Now, why is the first one a parentheses and not a bracket? There you go. That is telling you that that -2 is not to be included. Now, here's a question for you. We know that we're going to include the 4 because there definitely is a closed circle at the other end of that. What if your graph, your function, just did that? What if it just stopped? There wasn't anything at the end of it. Here's the question. Would you still include it or would you not include it? Let's see. How many people think they would not include it? How many people think you're going to include it? How many people are not going to vote? There we go. Okay. You would still include it. There has to be something on the graph to tell you not to include it. Typically, it's an open circle. If you're dealing with rational functions, you're going to see asymptotes. There'll be something there. Okay. Good, good, good. Now let's go ahead and get the range out of the way. So if the domain is how wide, well, the range is just how tall. So see, again, we have set boundaries. So what's the lowest the graph goes? Okay, so -5 to what? 3. What am I going to put on the -5? Bracket. What about the 3? Parentheses. There we go. So this grid, or should be this graph, only exists horizontally between -2 and 4, vertically between -5 and 3. That's all domain and range is. Okay. What are all the values associated with it? Okay. What's it asking us to do in B? Like f of 0. What's it giving us? There you go. Now normally you would take that value, substitute it in, and simplify, but we don't have the equation that accompanies this. We just have the graph. So basically they just want you to get the idea that they're giving me a 0 here, but what's the corresponding y value that goes with it? So I'm going to come over here along the x-axis. I'm going to locate 0. Okay. Now, depending on if the graph is above or below, I'm going to go straight to the graph and then to the y-axis. But this one is kind of an exception because as soon as I hit the graph, see, I don't have to move horizontally because where am I? I mean, I'm on the y-axis already. So in fact, what corresponds when y is 0, or should I mean, when x is 0? -3. So f of 0 is -3. So really, you're just looking at a relationship between the x's and the y's. You know that that would be an ordered pair on the graph. Okay. Now, you don't have to go ahead and write the ordered pair out. I mean, the answer is -3, but if it helps you to kind of make that relationship a little more concrete, you know, I mean, there is a point to it. There is a point to it. It's a point, coordinate. Alex got it. Okay, yeah. Moving up. If you love that one, you're going to love the one I have coming up. Okay, f of 2. Okay, so somebody help me out. When I find 2, am I going to go above or below? Okay, so I'm going to go all the way down. As soon as I hit the graph, I'm going to go straight for the y-axis. So what do you think I'm looking at here? I'd say -5. So what's the value of the function when x equals 2? That's f of 2. Well, we got -5. Okay. Can anybody help me out with f of 4? -3. There we go. Not only do we see that point right there, but if at 4, I go straight down. As soon as I hit the graph, I go over. There's -3. Okay. Question. Yes, ma'am.
How do you decide if to go down below or up?
Oh, it depends on where the graph is with respect to the point. Like, for example, what if I wanted, and I'm not going to worry about -2 because that one has an open circle. What if I were to ask you f of -1.5? So see, here's -1, so -1.5 would be right here. So see, with respect to that point, the graph is above it. So here I would have to go up, and as soon as I hit it, I would go straight over. Okay. Does that make sense? Okay. Cool. All right. Good. So any other questions on that? Pretty easy? Okay. We function well in our domain? That's not even the one I was talking about. That's a freebie. Okay. All right. Let's take a look at this next set of problems. Given the implicit equation below, find the explicit form and use a graphing utility to determine whether each relation is a function by applying the vertical line test. And then we're going to sketch it. Now, we're going to sketch it by hand. We're not going to use the calculator, okay, because we can use our previous skills that we learned. Now, when it says explicit, what do you think that means? Okay. Now, what that means is we want to take the equation and we want to solve for one of the variables. Okay. Right now, they are implicit because it is not solved for either variable. And typically, what do we like to solve for? Y. We want it to be y equals, because again, it goes back to that relationship. Y is a function of x. Y depends on x. So that's what it means when it says find the explicit, solve for y. Okay. So walk me through this. How would I get this to be y equals? Okay, so first I would go ahead and move this term, so I'm going to add it, plus x squared, plus x squared. Remember, whatever you do to one side, it's got to be done to the other. It has to maintain that balance. So 2y is equal to x squared plus 4. Now what? Divide by 2. There we go. So 1y equals the 1/2 x squared plus 2. So there's my explicit equation. Okay. Now what's the parent for this guy? Y equals x squared. Now remember, I just drew him a moment ago. X squared starts with the vertex at the origin, kind of looks like that. Well, what's the plus 2 going to do to that guy? Okay, it's going to shift everything up 2. That's a vertical translation. So I know from 0, I'm going to move up 2. But now, the 1/2 is what we refer to as a dilation. What does that mean? Something about the graph is going to be changing. There you go. So we're talking about the size and or shape of the graph changing. That means an expansion or a compression, basically stretching, shrinking. Is this vertical or horizontal? This one's vertical. Think about if you were to plug a value of x in. Let's say I plug in x equals 1. Well, what would be the first thing you do, according to order of operations? So you square it. See, once you've squared it, that's the one function that determines, what your parent is going to be for this particular graph. It's no longer an x value. You're now affecting the y values. So you would have to change x if it was horizontal prior to the square. Okay, so we're taking all those y values, we're moving them up 2. So this is vertical. So imagine this guy right here. Is that a stretch or a shrink? 1/2. It's a shrink. The y values are going to be half of what they originally were. So imagine this parabola right here. If I could put my hands above and below, if it were tangible, if I just started squeezing it, what's that going to do to the graph? Is it going to make it more skinny or wider? It's going to make it wider. Okay, so we're probably, looking at something like this. I think I made that a little too wide, but that's okay. Remember, these are just sketches. I mean, if you really want to, you could plug in points and get your exact ones. That's fine. Okay. But now, let's use that vertical line test. So I've got a vertical line right here. I'm going to sweep him back and forth. Does he pass or no? He does. Now, how do I know if he fails? What am I looking for here? Yeah, there you go. Does the graph hit that vertical line in 2 or more points at any time? Because this doesn't, yeah, this guy's a function. Is he a relation? Yes. Now remember, no matter what, every graph you come across is a relation. It's just a collection of ordered pairs. But every relation is not always guaranteed to be a function. Okay, so he is a function. Good, 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 good. Let's try this one. X minus y squared equals 1. How would I get it y equals? What's the first step? Subtract x, okay. So minus x minus x. Now we're subtracting the y squared, so we don't want to forget about that negative. Equals, you can say negative x plus 1, 1 minus x, does not matter. Okay. What now? There you go. We got to get rid of the negative. So you can divide through, you can go ahead and multiply through, however you want to do it. So y squared equals positive x minus 1. Now we're one step away. How do I get a y from a y squared? Square root. There we go. So y equals the square root of x minus 1. But I can't help but feel that we're missing something. There you go. We solved an equation algebraically. If you take an even root, you want to put the plus minus in front of it. So we actually have 2 different graphs here that are going to combine to give me 1. We've got the positive radical, and then we've got the negative radical. Okay. So what parent is this guy coming from? Yeah, square root of x, right? So let's look at the parent for just a second. What's square root of x look like? Can anybody show me the motion with their finger? There you go. A lot of people are, doing this in the air. It's half a parabola, right? Probably going to look something like this. That's the square root of x. But we want square root of x minus 1. So what's that going to do to this parent? Now, is it a vertical or a horizontal shift?
To the right.
To the right one, wait a minute, it says minus.
Well, if it's the X is opposite.
There you go. The X's are always trickier. The horizontal is much trickier than the vertical. If you're adding or subtracting from X, you take the opposite. So it would move me 1 to the right. It would look like that. So this is the square root X minus 1. Okay. Now, what if I wanted to go left? Square root of X plus. There you go. Okay. All right. Now, well, that's the positive. Now I want negative square root of X minus 1. Well, what's that negative going to do? It's going to flip it. What do we call that in mathematics? Reciprocal reflection. There we go. So this will just reflect it with respect to the x-axis. So this is negative square root of X minus 1. Okay. There we go. So now I'm going to take my, let me go ahead and move this back. I'm going to take my vertical line here, moving it back and forth, and you see pretty much everywhere what's happening. Okay, it is not a function. Not a function. Not function. But it is still a relation. Remember, everything is a relation. It just may or may not be a function. Okay. Anybody having a hard time so far? Any questions? Yes, ma'am. Oh, I thought you went like that.
No, I'm not understanding.
Oh, you're not understanding? Okay, what can I do to help you out?
It's okay. I'm coming for cheaper.
Are you sure? Okay, all right. Well, I know what you're saying. Mr. West, this is just, we want something a little more challenging. I hear you. I hear you. Okay. Let's try this one. I forgot to erase that. Okay. X squared equals 2xy plus 1. Okay, so what I want you to do first, take about 30 seconds to solve this for y. Okay, and then I want to see if anybody can recognize what we have. The first one was a quadratic. Second one was a rational. Oh, dadgummit. It's rational. I got so excited I just spit it out. Dadgummit. Oh well, what are you gonna do? Second one was radical. Yeah. Guess you guys can't blame me. It's hard to get excited, you know. Math, I mean, whoo, you gotta get excited, right? I can just tell by all the people yawning right now. Fuck's ready to go. All right, well, since I kind of screwed that one, just walk me through how would I solve this for y? What would I move first? Okay, let's get rid of that 1. So minus 1, minus 1. Opposites cancel. X squared minus 1 equals 2xy. There you go. Now, even if it means we have to divide by a variable, that's perfectly fine. We want to isolate y. So I'm going to go ahead and say 2x. Now, for this one, I'm not going to divide each one individually because it's going to be better to look at it as a single fraction. So I have y equals x squared minus 1 over 2x. Okay. This is going to be a rational function, which means we're going to have what? Starts with an A. Asymptotes. Okay. Those are values that the graph is going to get infinitely closer to, but never do what? It's never going to touch. Okay, now, we actually have a unit on this coming up. We're probably going to be spending at least a week, week and a half on graphing rationals, solving rational equations and inequalities. So I'm not going to cover everything at this point, but I'm going to go ahead and bring up the most important ideas. Okay, we're very interested in the values of x that are going to make both the numerator and the denominator 0. Okay. First, let's start with the values of x that would make it undefined. What am I saying when I say that? That's exactly right. Philip, say it again. The denominator will be 0. What values of x would have me dividing by 0? Well, what's the only value of x I can't have? Okay, so x can't be 0. So that tells me immediately I have a vertical asymptote right here at x equals 0. In fact, that's a pretty good hard and fast rule. Okay, any value of x that makes the denominator 0 is going to become a vertical asymptote. Now, there are exceptions. You could end up with a removable discontinuity. That's something different, okay? So I'm not going to say that every value of x that makes the denominator 0 becomes a vertical asymptote, but the majority of them will be, okay? Now, would this function have a horizontal or an oblique asymptote? And what am I talking about when I say oblique asymptote? Slant. So oblique is the mathematical term for a slant asymptote. So what do you guys think? Would we have a horizontal or a slant? How many people think horizontal? How many people think slant? There's a lot of people not voting this time. Okay. But more people raised their hand on the slant, and that is correct. This is going to have a slant asymptote. Can anybody tell me how by looking at this expression I would know that? The x squared on top? Well, I mean, we could have an x squared on top, and it could be a horizontal. Like, what specifically tells you that? Oh, say it, William.
Oh, there's a greater degree.
There's a greater degree. The degree is what we call the powers. Okay. Now, again, I'm not going to go into this in a lot of detail yet, but if the degrees are the same, that means the largest powers are the same, you'll have a horizontal asymptote. If the degree of the denominator is larger, you'll have a horizontal asymptote. If the degree of the numerator is larger, you'll have a slant asymptote. And we're going to cover those three cases again later, so don't worry about, hanging on to that right now. Okay? So what we need to do is figure out what that slant asymptote is going to look like. So I'm going to take 2x, and I'm going to divide it into x squared minus 1. You guys remember long division? Or you may even use synthetic division. We're actually going to use both. I'm just going to go ahead and do long division today. Okay. Now, you may or may not remember, if there's a term missing, you see how it goes right from x squared to 1? There's no x to the first term. If a term is missing, you have to account for it with a 0 coefficient. So I'm going to say plus 0x minus 1. Okay. So 2x is my divisor. X squared minus 1 is my dividend. What do we call the answer I'm going to get? That's the quotient. Okay. Well, just think about how you'd use long division of numbers. Okay. I need to match up this first term. 2x times what would give me x squared? Now, the x times x will give me x squared, but that would be 2x squared. How do I get a 1x squared? 1/2. See, once you figure out that first term, now you multiply it. That gives me x squared. And remember, we subtract. Whoa. I think I'm touching the screen there. So those are going to cancel. And then I would bring down the next term. And then I just start the process over again. So 2x times what would give me 0x? 0. So I'm going to go ahead and say plus 0. Okay, so that's 0x. Okay, bring down the minus 1. Now, we don't need to go any further than that. What would we call the minus 1? That's the remainder. Okay. Now, typically, in calculus, there's a way to go ahead and write it. There are forms that you're going to use when you're analyzing these, but I typically say, once you find the remainder, you can go ahead and stop, because I just need to know what the slant asymptote is. So it is a linear function. You don't need to put the plus 0, even though we know that would be your y-intercept. What's the slope? 1/2. Okay, I'm going to use the rise over run, so from here I'm going to go up 1 over 2. Up 1 over 2. Okay. There we go. There's my slant asymptote. Now, don't worry if, again, you're sitting out there and you're like, I don't know what he's talking about. We will take the time to go over these in a lot of detail. Okay, think of this almost as a Reader's Digest version. There's a lot I'm not mentioning. Okay, if you're having trouble with the long division, don't worry, we're going to have practice. Okay, that's even why I wear glasses. It helps me with division. It helps me with division. Ah, there you go. Yeah, you get it. Okay. Now, all we have to decide is, where will my branches go? Now, all we've done so far, we've got the slant asymptote. We found the values of x that are going to make the denominator 0. Well, now we want to find the values of x that will make the numerator 0. So I'm going to say x squared minus 1 equals 0. Okay, so walk me through this. How would I solve that? Okay, plus 1. So x squared would equal 1. Okay, I'd have to take the square root, right? So x equals what? Good, not just 1, plus or minus, because we're solving an equation and we took an even root. Okay. Now, you may or may not remember the values of x that make the numerator 0. Those will be your x-intercepts. This will tell me where it crosses the x-axis. So I know the graph should be crossing at 1 and -1. Well, see, we don't need to go any further. Do we know where my branches have to go? Okay. Look at the left of the vertical asymptote. You notice how that point is also above the slant? So its position tells me there would have to be a branch right there. Where would the other branch have to go? On the top right or bottom right? Where would it go? Bottom right, because that's going to be below the asymptote. So probably it's going to look something like that. Okay. Now, if you were wondering, okay, how close were we? Here's the graph of it. So we actually did really well, right? Okay. So that's pretty rational. Okay. Now, here's my question. Yes or no? Is it a function? Yes. Now, you'll notice, even if you look at the technology, these two parts right here, it looks like it's going to be touching that axis, the y-axis. Okay, but remember, there's always going to be an infinitely small distance between the two. They will never make contact. So this guy is a function. Yep. Okay. And there's one last concept I want to talk to you about today before you leave. Increasing and decreasing. Okay. So again, if it helps in the beginning, kind of think of this in terms of slope. Okay. It's going to decrease if it falls to the right, has a negative slope. It's going to increase if it what? How do you know you have a positive slope? It goes up to the right, okay? Or if it's constant, it remains the same. So we want to go ahead and tell where it's falling, where is it decreasing, rising, or increasing, okay? So look at this graph right here. Look at the y values. Is there any place where you would notice a negative slope? You wouldn't? Any place that drops to the right? Doesn't that one drop to the right? Okay. Now, the y values are what we're looking at, where the y values are dropping or increasing. Okay. But we describe those locations using the x-axis. So where does it start falling? It starts at -1, right? Where does it stop falling? X equals 1. So we would say it falls or decreases from x equals -1 to x equals 1. We look at where the y values are increasing or decreasing, but we describe it using the x's. Okay? And you'll notice what happens at x equals 1. What do the y values do? They're staying the same. They're remaining constant. So it starts at x equals 1 and goes all the way through what? X equals 5. Okay. Now, what do you notice happens at x equals 5? The y values begin to increase. In fact, they increase until what? X equals 7. Now, this is a way to kind of verbalize this. Technically, what we would do, and the answer I'm going to be looking for, we would go ahead and use interval notation to describe these locations where it's increasing, decreasing. Okay, so look at the decreasing. We said from -1 to 1. Would everybody agree if I wrote it like this? Okay. But here's the one thing you don't have to worry about, and it's only this particular topic. When you're talking about decreasing, increasing, or constant, you do not have to worry about inclusion. That means parentheses and brackets make no difference. I could write this same answer as -1 to 1, and it's perfectly fine. When you're increasing, decreasing, or constant, you're not concerned with is the value included or not. Now, domain and range, absolutely. Yeah, parentheses, bracket. But here, if you were to go ahead and give me that answer, I'm not going to count off for that. Okay, it's equivalent. Just want to throw that out there. All right. Now, also, you notice how I've been kind of talking about it in terms of slope? Well, let's say you don't have just straight segments. Think about a parabola. Are there places where this graph could increase or decrease? Yeah, think about this line of symmetry through the middle. As you're moving from left to right, what are the y values doing? So here it's decreasing, but what happens as soon as you hit the vertex? It rises. So I was just kind of using that analogy of the slope to kind of help you get the idea. Okay. Any questions? Anybody having a hard time? Okay. Well, hopefully you'll come in and I'll set you straight. All right. Well, thank you very much, guys. Appreciate it. Looks like, ooh, that bell's about to ring. My goodness. Okay, so first thing we will do tomorrow when you come in, we will have our quiz. And then we'll go ahead and continue. Okay. All right. Thank you, folks. You have a great day. I'll see you tomorrow. I'm here at 7:45, and I believe some people wanted a pass.